Anything confusing about that? Any questions? Yeah? Well, it's not even a range. It means that one of them is arbitrary. So like x is arbitrary, then it'll determine y. If y is arbitrary, then it'll determine x. So what it determines is the ratio of x to y. So if I said x equal to 1, in this case, it'll turn out that y is equal to minus 1. If I chose an x equal to 2, y would have turned out to be minus 2. If I chose an x equal to 3, then I would get y equals minus 3. You can work through the equations and see that. And the reason why that happens is that if you look at these equations, we can't actually see it here, but with the eigenvalue and eigenvector, and I'll show it to you later in a different context, you'll see that you don't really get two independent equations. The equations turn out to be a multiple of each other. And because of that, you can only solve one of them, and the other one doesn't give you any extra information. Okay. So now we're going to formally try to understand what's going on with this equation in the context of just a general 2-by-2 matrix, where matrix A has elements little a, b, c, and d. So we'll set up this equation. Okay. So key to all of this is the matrix I, which is the identity matrix. And in 2 dimensions, that's what I looks like. And sometimes people might write a little 2 there if it's not clear how many dimensions you're working in, and they would specifically want you to think about that. But in general, you know how many dimensions you're working in, and in 3 dimensions, so I3 would be equal to 1, 0, 0, 0, 1, 1, 0, 0, 1. The identity matrix is the matrix where only the diagonal elements are defined. I subscript n is equal to 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. And then the second last line would look like this, and the last line would look like that. And this is the diagonal. So everything's 0 below the diagonal, and everything's 0 above the diagonal, and then just the diagonal has 1s. That's called the identity matrix. And you can write it in any number of dimensions. And the thing about the identity matrix is that I times a vector just gives you the vector. I times a matrix just gives you the matrix. The matrix times I also gives you the matrix, and so on. So it's like the generalization of the number 1. Remember I told you that A times B is not always equal to B times A, and we discussed that. But if you're multiplying by I, then you can switch them around, the order in which you multiply. Okay. So now we have this equation, A times V is equal to lambda times V. So can anybody express that equation in words? What is that equation asking us? So if we're doing it in 2 dimensions, it's asking us, is there a vector v through the origin? This could be, let's say that's v1. That's v2. That's v3. Now v, how do you write down v? Well, you write down v in terms of x and y. But since v is defined by just one point on it, we can say, okay, let's say we'll choose x equal to 1. So we'll say v is equal to 1, and then you look at the value, the corresponding value of y. So if this is x equal to 1, then that's the corresponding value of y. That would be the corresponding value of y. That would be the corresponding value of y. So that would be y2, this would be y1, and this would be y3. So if we wanted to find v, we can just choose an arbitrary value for x and see what the corresponding value for y is. Or we could make y2 equal to 1, y1 equal to 1, y3 equal to 1, and then write down an x2 or an x1 or an x3. What's important is just that ratio, and that ratio will determine the slope of these vectors. And what this says is, can I find such a vector that if I take that vector and multiply it by a, it's the same as taking that vector and multiplying it by a number. Now, in general, if I take a vector, let's say I take the vector v equals 1, 1. So that means I'm looking at this point, 1, 1. This is my vector v. And let me take a matrix, and let's say I've got a matrix A equal to 0, 1, minus 1, 1. And now I take A times v. A times v is going to be equal to 0, 1, minus 1, 1 times 1, 1. And that's going to be equal to 0 times 1 is 0, 1 times 1 is 1. So I'm going to land up with a 1. And then I'm going to get minus 1 times 1 is minus 1, plus 1, I'm going to land up at 1, 0. So that means if I started out over here, the next point is going to be over here. So taking a point in the plane and multiplying it by a gives you another point. Is this point on the same line as this? In other words, if I took this point, 1, 1, and multiplied it by lambda, I would get lambda, lambda. And if lambda is, let's say, 1.5, then I would land up there. So if I'm on the line and I multiply by a constant, I say on the line. If I'm on the line and I multiply by a matrix, then I could land up anywhere else. What this equation asks of us is there a line there such that if you start on this line and multiply by the matrix, you'll always stay on the line? Does everybody understand that? Or is it going above some of you? Just you work it out at home when you read through it. Who plans to work it out at home when they read through it? Okay. Who's following in class? Okay. Any questions to help you follow in class? Okay. turns out that this stuff is really useful. Otherwise, I wouldn't do it. I'm not trying to bore you with math. I'm trying to improve your math skills so that you can do interesting things with it. Okay, so A times V is equal to lambda. And now remember I said that if you have a vector, you can also pre-multiply it by the identity matrix. It's the same thing. Now you might say, why do I do this trick? The reason why I do this trick is that if you look at this equation over here, this equation is a 2 by 2 multiplied by a 2 by 1, which gives you a 2 by 1. So that means a 2 by 2 matrix multiplied by a 2 by 1 vector gives you a 2 by 1 vector. So this represents a vector with 2 rows and 1 column, 2 rows and 1 column. This is a matrix times a vector. This is a scalar times a vector. But if I put this in front and then I isolate this, I turn that into a matrix. So lambda is a number, but if I multiply lambda by I, then I get something that looks like this. So the reason why I do this is that I want to turn this number into a matrix. The effect of this in multiplying V is exactly the same as just multiplying it by a number. And the reason why I want to do that is that if I subtract these two sides, AV minus lambda V like that, then because this and this object, this is a 1 by 1 object and this is a 2 by 2 object, they can't be brought out in common and subtracted. But if I write it in this way, A times V minus lambda I V, and I say this is equal to 0, I'm taking this onto the other side. So this equation here is I can subtract both sides by this quantity or this quantity, and I can get these two equations. This equation I can't do anything with. This equation, I can write the A, I can take the V out as a common factor, and I can say A minus lambda I times V equals 0. Does everybody see why I did this and now what I can do? So if I've got a number, I turn it into a matrix. The fact that I turn it into a matrix is that when I set this up, I've got a matrix minus a matrix. I told you can only do subtraction if the dimensions of the objects you're subtracting have the same dimension. So that's sort of a little trick, but it's mathematically legitimate. Okay, so now, when I solve scalar equations, if I say some constant A times some number x is equal to 0, what does that mean? What's the solution to that equation? Huh? Either A equals 0 or x equals 0, right? So if A is not 0, then x equals 0, right? So it could be that it's either the null solution or any x will do if A is 0. Now don't forget the second part, that any x will do as long as A is 0. Now I've got a matrix equation like this. Now remember we talked about AX equals B, solving this equation. What I said is that this has a unique solution. If A to the minus 1 exists, then A to the minus 1 times A times x is equal to A to the minus 1 times B. And then this is just equal to I times x, because that's the definition of an inverse, is equal to A to the minus 1B. And x equals then A to the minus 1B, because the identity times x is just x. So here, you have a solution, x equals A to the minus 1 times 0, if A to the minus 1 exists. And if A to the minus 1 doesn't exist, then any x will do. Now here, if A to the minus 1 doesn't exist, then it turns out that this will have a solution that is non-trivial. If A to the minus 1 does exist, and B is equal to 0, so if B is equal to 0, then this implies x is equal to some matrix times zeros, then x will also be equal to the trivial or the null solution. But if A to the minus 1 does not exist, then you have a chance of getting a solution that is not trivial. And in this case, in a 2 by 2, you can get a solution that defines the direction, where x is a multiple of y. So what we have to make sure is that A is not invertible. The inverse of A doesn't exist. What is the condition for the inverse of A not to exist? Or A has an inverse provided what? Provided the determinant is not equal to 0. Therefore, if the determinant is equal to 0, we can get a non-trivial solution to this equation. So let's go through that process. That's sort of the logic behind this. Once you've comprehended all this, and I know it takes a bit of time, and in the textbook you can work through as many or as few examples as you need to sort of get a grip on what's going on, it actually turns to be immensely elegant. Okay. Who's excited about seeing the solution to this? Come on. This is kind of the mysteries of the universe unfolding before your eyes. Why does mathematics work? So, in quantum physics, for example, physicists were trying to discover the nature of matter and the structure of the universe. And they had all these different ideas, and they didn't know exactly how to pursue them or develop them except using mathematical arguments. And they had different ideas, and different ideas led to different theories, and each theory could be developed using mathematics, and those that did not fit the data were thrown away, and those that did were kept. And so they developed ideas in quantum physics and particle theory, and they said, okay, if we make these assumptions, and we apply the mathematics, and then we measure things, this is what we should measure. So when they measured things and they found out certain things, they could throw some ideas away and they could keep others. The only reason why they could keep them is because models predicted them using mathematics. And then models predicted all sorts of things, like when Dirac worked on quantum physics, and he wrote mathematical equations and came up with a solution, and that solution, its interpretation is there must be something that is exactly the same as an electron except positive. And so he thought, no, this can't be, my mathematics must be wrong, or my model must be wrong. And then the physicists found something called the positron. And there have been many crazy ideas that have come up in modern physics. And people would have just thrown them away if it wasn't that they were mathematically consistent. And yet, time and time again, the mathematics reveals something about the structure of nature. So one physicist said that it's unreasonable that mathematics actually works so well. So mathematics actually reveals things about the structure of our universe. And as we go through, and it's very elegant, and to people who like that sort of stuff, it's actually quite beautiful. And it's unreasonable, and we don't know why. And that's what gives it a lot of its charm, is that, wow, there are these beautiful things and they work, and they describe nature. And early on, we looked at the Mandelbrot set, and we talked about that. And that was something rather surprising and that came purely out of mathematical computations. Okay, so let's work out this equation. If I've got a matrix A equals A, B, C, D, the eigenvalue equation says, if I've got a matrix A and I multiply it by some vector V, then that's the same as multiplying it by some scalar V. So does such a V exist and does such a lambda exist? And so when I came to the Impala equation, I could ask that. And with the Impala equation, it says, yes, there is a direction, and the direction is 45 degrees. And there is a lambda, and the lambda is 1.2. That corresponds to, if this is the matrix A, then there is a vector 1, 1, and an eigenvalue 1.2 for which this equation holds. So we demonstrated it, and now we're going to try and find it. So we're starting with the equation, and we're saying, how do we solve this? And the way we solve it is we said, this is equivalent to saying A minus lambda times the identity matrix times V is equal to 0. And if A is invertible, then V is equal to 0 is the only solution. But if the determinant of A minus lambda I is equal to 0, then it's possible that I can get a non-trivial solution. So if I'm looking for a non-trivial solution, this is where I say, start. I look at this equation, the determinant of A minus lambda I equals 0. Do I have solutions to this equation? If I have solutions to that equation, then they're candidate values for lambda. And if I know the lambda, then I can look for the corresponding eigenvectors. We saw that. If I give you the lambda, find the vector. If I give you the vector, find the lambda. So, if I'm going to find a solution for which V is not identically 0, so I'm not interested in the identical 0 solution, because the 0 solution is the one that just sits here and doesn't define a direction. Any other solution defines a direction, but the one that sits at the origin doesn't define a direction. Okay? So, what is the determinant of this? So firstly, what is this matrix? This matrix is A, B, C, D minus lambda, 0, 0, lambda. And so I'm interested in the determinant of this matrix minus that matrix. If I subtract these two matrices, so how do I subtract matrices? How do I subtract these two? What's the rule? The rule is to subtract element by element. So that means A minus lambda, B minus 0, C minus 0, D minus lambda. And the determinant of this must be equal to 0. Now what's the determinant of this matrix? How do I find the determinant of that matrix? Remember, it's just the diagonal elements. It's just the determinant of the matrix is this times this minus this times this. So it's A minus lambda, B minus lambda, minus BC equals 0. Now I can multiply this out. If I multiply this out, I get minus lambda times minus lambda is lambda squared. Then I get minus A minus plus D lambda. And then I get plus AD minus BC equals 0. Okay? Yeah. In the lecture notes, let's see. Minus BC. AD minus BC. Oh, AD minus, yeah. It may be correct in the textbook, but yeah. So that looks like, I'll just have to check that. I hope we corrected in the textbook. As I said, these were prepared before the final corrections. Okay. CB, yeah, CB. Okay. So, this is called, so if we have a look at this, this is actually the determinant of the matrix A itself. And this is something called the trace of the matrix A. The trace of the matrix A is just the sum of the diagonal elements. So the thing is that we've got lambda squared minus one constant plus another constant equals 0. This constant is called the trace of A, and this constant is called the determinant of A equals 0. And if you don't like using this, you can just keep those elements. It just turns out that the trace is a particular characteristic of a matrix, and the determinant is a particular characteristic of a matrix. So if you have a look at this, you say, I have here a quadratic equation in lambda.